Hello and welcome back to another video with It's Dr. Dan, and today we're going to be going through how to balance redox reactions, specifically in basic solutions. So whenever it comes to trying to balance these in basic solutions, these can be some of the most complex redox reactions, just being that it involves an extra step, being that we're in solution, right? So it should be in water, but we're going to be adding that base component, maybe something like sodium hydroxide or like barium hydroxide or some kind of strong base that's changing the pH of the solution, therefore helping the electrons be transferred. And that's going a little bit more detail than what we need. So we're going to go through exactly how we're going to do these and what do these look like. So typically whenever we have these kinds of reactions, you're going to see an imbalance of charge on the left and the right hand side of the problem, meaning that no matter how many coefficients you add, it's not going to generally fix what that charge is in any simple means. So what we're going to have to do is add waters and hydroxides and different things to it in order to balance it. And the whole reason for this is because of it being an oxidation and reduction reaction. We're going to be doing that whole entire Leo goes grr, right? Thinking of our growling lion. So Leo meaning loss of electrons, and the other thing going through gaining electrons. So we're going to go through the exact steps of how to do this. And then at the end of the problem, I'll show you the entire summary of all of them. So let's go through and see what kind of problem this would look like. So this kind of problem would look like something like this. So we would have complete and balance the following equation in a basic solution using the half reaction method. So as you can see, we have NO2 being added to aluminum to make ammonia and then aluminum hydroxide. So with this one, you can see that there is a charge imbalance. There's charges on different species. Things don't quite match up. I'm also asking, can you label the oxidizing and reducing agent as well, just to practice the whole complete picture? Now, keep in mind, this could be shown in a couple different ways in a problem. It could be listed out in the problem like this above. Sometimes you might have it where it says in a basic medium. This is just the same idea of a solution. It's just another way of writing the same idea. The other way too is that sometimes you'll see it where it says basic over the reaction arrow as well. There's three different ways to kind of try to give you that hint of, hey, you need to do the half reaction method in order to balance this in a basic medium. So let's go through our steps. And we're going to be following our general set of rules for how to label an oxidation number. So when we have, let's say, the following formula like we had before, we're going to be going through each of the different following rules to try to help guide us. And a lot of these is kind of like putting them to memory. So, for example, like fluorine is always -1, oxygen is generally -2, hydrogen is generally +1. But there are some little exceptions as well. So, we're going to try to remember all of them. So, let's say for the first one, right? The first thing is keeping in mind that the sum of the oxidation numbers must be equal to the charge of whatever the ion is. So, we see we have this -1. So that must mean the entire thing must be equal to -1. So we know that every oxygen is equivalent to -2. So the way that we'll end up kind of writing these is I write like a little little t for myself to do some math. So if I have two oxygens, each one's -2, that means the total on that side is -4. So in order for it to equal that -1, that must mean that nitrogen has to be +3 in order to make that math work out. Now we'll move over to our aluminum. And with that one, right, it's one of those elements that's completely by itself, right? So it's its natural form. So whenever we have something by itself, that means it's going to be a 0. Now we'll move over to the next one, and we can see that whenever hydrogen is bound to a non-metal, it's going to have a +1. So we can kind of do the same little t here. So we know we have 3 of them, so that means overall it's +3. So what we need to do in order to balance that is nitrogen needs to be -3. So we have that one. Now with this one, the aluminum hydroxide, this one's a little bit trickier, being that we kind of have a polyatomic bound to this, and then we also have the overall charge too. So we got to kind of keep everything in mind while doing this. So hydroxide in its own right is -1. So the way we can kind of view this thing is being that there's 4 hydroxides, right? So each one of them is -1, meaning that will tell us that aluminum is going to have a +3, being that every single hydroxide, OH, is going to be -1. If we want to go further and trying to label everything, we can, right? Keep in mind hydrogen is +1, and being that a hydroxide is -1, that must mean that each oxygen is -2. All right, now the tough part is labeling our oxidation reduction. So we're looking for anything that's changing charges going from the left and the right. One of those is that we can see is the nitrogens, right? We can see nitrogens going from +3 to -3, meaning it's becoming more negative or it's gaining electrons. So if you remember GR, right? Gaining electrons means reduced. Now we're going to look for what's being oxidized. So we're trying to look for what's losing electrons. And we can see that the aluminum is going from 0 to +3. So therefore, it must be losing 3 electrons in that process based on what we have right now. Okay, so that is our oxidized. All right, so aluminum is being oxidized, nitrogen is being reduced. Now, when it comes to labeling, our first question, which was what's the oxidizing agent? What's the reducing agent? Remember, it's like an agent of chaos. So it's something that causes something, causes the chaos. So the oxidizing agent causes oxidation, being that these reactions are in a pair, right? When we kind of look at them, right? So even though nitrogen is being reduced, NO2 is causing aluminum to be oxidized. So the way that we're going to look at this is NO2 is going to be our oxidizing agent. So it's the whole molecule instead of just an element. Therefore, when we look at this, aluminum is causing nitrogen to be reduced. So therefore, this is our reducing agent. Okay, so now our next step, in the step number 2, is we're going to write out our half reactions, which are going to emphasize the oxidized and the reduced parts of the reaction. Now, when you do these, you could technically skip the first step if you wanted to. I really only would recommend it to people who have a lot of practice. The big thing is that they have to kind of match like the metals or like whatever the other element is in each one of them. Like for example, like aluminum, you can see on both sides of the oxide, so you know those are going to go together. Same with the nitrogens. But it's usually good practice to label them, being that you have to be able to label these on any type of exam or quiz or homework. So we're going to write the half reaction for each one. So we'll start with our oxidized, right? We can see aluminum is turning into aluminum hydroxide, right? And we have that negative charge on it and it has a minus on it. All right, and that's the big thing is write down all your charges. I can't tell you how many times I actually make a mistake on these because I forgot to write a charge. So that's going to be the oxidized. So we'll label that so we can remember that for later. And then for nitrogen, right, we know that's going to be the reduced one. So it's going to be NO2. Aqueous is going to be turning into NH3. And notice that I kind of almost forgot my charge on the NO2. So like I said, write everything down. It's really easy to do. And this is our first step, right? Pretty easy. Now we're going to go through our balancing. So what we're going to do here is I'm going to just take one of these and we'll kind of do like step by step. And then we'll like kind of do the fast. So I'll show you like the faster way to kind of remember the entire balancing. So we'll start with the aluminum hydroxide, just being that's on top here. No particular order. It does not matter which one you start with. And then we'll do the NO2 next. Okay, so let's go to our next step and show how aluminum into aluminum hydroxide will be balanced. Okay, so step number 3 is we're going to balance all other atoms, meaning anything that's not hydrogen or oxygen, being that these are what's going to be pertaining to our solution. We will balance everything else. So in this case, that would be aluminum, being that's the only thing here that's not oxygen or hydrogen. And what you can see is that we have one on each side. So we're already done the first that third step. That's pretty nice. So, but the next step is when the real challenge starts. So where we're going to add water in order to balance oxygen and then H plus to balance the hydrogens. So when we're kind of looking at this, I got to examine it and see like, oh, hey, do we have any imbalance of oxygen here? And what you kind of will notice really quickly is that, hey, we have those 4 oxygens on the right-hand side. So what we need to do is add 4 waters in response to that on the left. So that balances our O's. But now we have an imbalance of hydrogen, right? We had 4 already on the right. Now we have 8 on the left. So what we're going to do is we're going to add 4 hydrogens to the right-hand side in order to balance all of the hydrogens. So keep in mind, you got to add up all the pieces, right? We had the 4 H's and then the 4 that were in hydroxide. Now, our next step is balancing our charges. So we're going to add electrons in order to do this. So the thing I like to do is I like to try to add up all my charges, like, and kind of put a number underneath. So like, for example, I have 4 hydrogens, that's 4 plus. On the aluminum hydroxide is a negative. So that means the entire right-hand side, I have 3 plus. Where on the left-hand side, I have an entire thing of 0. So what we're going to do is we're going to add 3 electrons in order to balance that charge. So we have 3 electrons on the right-hand side that I just added. So what that does is that's going to then cancel that. So now what we're going to do is we're going to do the same thing with the other side of the half reaction. So this is one of our answers, but we're not going to be done even after that step. We have a few more steps to go. All right, let's do the other half reaction. All right, so we're going to do the other half of this reaction, but a little bit quicker. So that way you can try to remember the order for when you're going to do this. So this is where I'd recommend maybe pausing the video and see if you can do this half reaction on your own and then watch my explanation of it. So the first thing, what are we going to do? Is we're going to balance the other atoms. So what do we have? Is we have nitrogen as our other atom in this case, and it's already balanced. So this is something that, oh, we have a little bit of an easier problem for ourselves. So now we're going to balance the O's. So we can see we have 2 oxygens on the left. So what do we need to do is we need to add 2 oxygens on the right in the form of water. All right. Now what we're going to do is we're going to balance our hydrogens by adding protons to this. So I have a total of 4. So we have 4 plus 3 hydrogens on the right. So we have 7 on the right-hand side. So I need to add 7 hydrogens to the left in order to balance this. Now, our next part is balancing our charges. So we have a total of 6 plus on the left, and we have 0 on the right. So what do we need to do is we need to balance that by adding electrons. I'm going to move this over, and we're going to add 6 electrons to the right in order to do this. And now we have our half reaction for the reduction part. Now this is when we add them together and try to cancel everything out. Okay, this is the part where we now multiply the half reactions to make the electrons equal in both. So on both sides. So notice how we have 3 electrons on the top here, and on the bottom equation we only have 6, or we have 6 total. So that doesn't show an equal transfer of electrons. So generally what we have to do is we have to usually multiply both of them by each other's electrons to kind of make them equal to each other, especially if it's like 2 and 3, for example. But in this case, being that we have 3 up here, well, how do I make it equal to 6? That's a little bit easier, is that we'll just multiply the top by 2, and technically, I guess the bottom by 1, right? We don't actually have to do any math there, but hey, we'll just kind of mention it. So we're going to multiply the top by 2. So when we do that, we're going to be kind of redoing our math here for all of our coefficients. So what I'm going to do is I'm going to move this guy down a little bit. And what that means is I'll have 8 waters. I'm going to have 2 aluminums, being that I'm multiplying everything. Then I'll have 2 aluminum hydroxides. And the big thing is here, what it's doing is it's going to keep everything charge balanced, but it's also going to make it so that our electrons will cancel later, which is our big thing, right? 8 hydrogens. And then we have our 6 electrons. Okay, so now we see our electrons are equal, which means that when we add these 2 equations together, that the different pieces are going to balance just like they should. So that means we can kind of, well, I guess we could just kind of keep that up here just to show our work. But, that's where you can kind of like cross that out. And then we have our complete parts. So let's go on to our next step. Our next step is that we're going to add our reactions together almost like a big math problem. So we're going to add up all the reactants, all the products. But the big thing is that we're going to cancel anything that's matching on the left and the right, almost like kind of like spectator ions from net ionic equations. So the first thing is like just to kind of point that out is like you can see that, hey, we have matching electrons on the left and right. So they have to cancel. That's a mandatory. It won't be correct without that. So we can see that the 6 electrons do that on both sides. Now, after that, we're going to cancel anything that's kind of similar, right? So we can see like water, for example, is matching. But being that we have an unequal amount, right, we'll cancel the little one. And so we have 2 waters canceling 2 of the ones on the left. So that means we have a total of 6 now on the left. We're going to do the same thing for the hydrogens we added, right? So we can see that, hey, we had 7 on the left, we had 8 on the right. So that's going to completely get rid of all the hydrogens except for 1 on the products. Now we can add up everything that's left. So what do we have, right? We want to make sure we're very careful with adding everything. It's very easy to miss something, right? So we have the 6 waters, the 2 aluminums, now NO2 minus, aqueous, and then we're going to add the 2 aluminum hydroxides. And we want to make sure that we get the subscript order correct. And then plus the NH3, and then plus the hydrogen ion. Okay. Now, one of the things that you might be kind of saying to yourself is like, well, is that entirely right? I thought this was a basic problem. So notice that this is the exact same process so far as an acidic medium, but there's one last step. Let's show the last step for how to balance this for a basic problem. All right, our last step, being that this isn't a basic solution, what we now have to do is we have to neutralize all hydrogen ions with OH minus, being that that's the main component of what makes a base, right? Think of POH or anything that's basic when you learn about acids and bases. So when we do this, we have to add OH minus to both sides, but it's all based on us trying to neutralize that proton that's here in the products. So being that we have 1 proton, what does that mean is we're going to add 1 hydroxide to both the left and the right. We got to do it to both sides. It's not just 1. So I'm going to add that above, right? Just to kind of show an example. So I'm going to add that to both sides. All right. Now, what does that mean? Well, what happens when you have H plus and OH minus together? They combine and they make water, right? They will make our water, right? What sustains life. So what does that mean is that we have a water now on the left instead of that H plus and OH minus that we had there before. So these will get converted. All right, so being that we have that water, what does that mean is, well, remember that whole entire thing with the left and right is we have to cancel that with what's on the other side. So when we do that, this one will go away. And this number over here will turn into a 5, right? And it will change. Now, the hydroxide that I kind of awkwardly wrote underneath, that's going to become a part of the problem. So what are we going to do is we're going to write down that we have 5 waters now, and this will be our final answer. And we'll put our liquid symbol. We have a hydroxide, right? That's an aqueous. Then our 2 aluminums combining with our nitrite, NO2 minus, aqueous. And that will turn into 2 aluminums, hydroxide, minus aqueous, plus NH3 aqueous. So that is our final answer to our problem. So notice that that is quite a bit of work, right? And it looks insane. So let's review all of our steps so that way you can write them down and you can try to do this on your own for your future problems. So this is all of our steps for how to balance a redox reaction in a basic solution. But keep in mind, I'm kind of missing that last step here. So let me scroll down here for a second. So the first thing that we're going to do is we're going to be determining the oxidation numbers. Now, the reason for that is if you have to label what's being reduced and oxidized, you're going to need to label them. That also helps you write out the half reactions, especially if you're kind of struggling to label them or just to kind of see the trends, then you definitely want to be able to label those numbers. Now, for steps 4 through 5, you can combine them in the one step. Most textbooks that I read usually do. So keep in mind that order. Other atoms, then you do oxygen, hydrogen, then electrons. So other, oxygen, hydrogen, electrons. Keep that order every single time. You'll be able to get it right. Now, from there, right, you're going to then multiply the half reactions to cancel your electrons. That will allow you to be able to add them together. And then once you do that, your last step, which sets this one different from everything else, is like when you try to neutralize, which I guess it would kind of help if I spelled that correctly. I just noticed. So when you neutralize any of these types of problems, um, you're canceling out the protons with hydroxide. So they cancel, right? And that way it's going to make water. So keep that in mind, right? That's the trick to the basic one. It's just one more step. So this is kind of now officially the hardest one, right? So you kind of go from this unbalanced form, right, where the charges are not balanced between the different ions, and then you can go to having hydroxide in the problem. You can see the basic component, you can see water, and then finally balancing it. And it is a very, very long process. So hope good luck on all these kind of problems. I hope that this video helped you. If this is your first time here, please hit that like button, hit the subscribe button, comment if you have questions, right? If anything is not clear or you're trying to figure out best resources to help you, please ask. Or if you have suggestions for future videos that you would love me to make to try to help you in your chemistry class. And if you're one of my students, send me a message. Please reach out for help. I would love to do that for you. Okay, thank you all. I hope you have a wonderful day, and I'll see you all later. Bye now.